Today, it's my great honor to have Professor Kim here today to give us a talk on how to automatically generate SystemVerilog model for an AMS circuit. Jeha is a currently professor at Seoul National University, Korea, and his research interests include low-power mixed-signal circuits and their design methodologies. He founded Scientific Analog in 2015, a company developing EDA tools for analog mixed-signal modeling and simulation in SystemVerilog. He received the BS degree in electrical engineering from Seoul National University in '97 and master and PhD degree in electrical engineering from Stanford University in '99 and 2003. Professor Kim is recipient of the Takao Sugano Award for Outstanding Far East Paper at 2005 ISSCC and is cited as top 100 technology leader of Korea in 2020 by the National Academy of Engineering of Korea. Thank you for being here, Jeha. The floor, or I should say, Zoom is yours.
All right. Well, thank you, Shahab, for the kind introduction. And hello, everyone. Thank you for joining this talk today. I'm Jeha Kim. And as Shahab introduced, I'm going to be talking about how to generate SystemVerilog model from analog mixed-signal circuits using a pipeline ADC example. Please don't hesitate to ask questions whenever you have it by typing into the chat window or asking in live. And I might be speaking in a little bit faster pace to cover all the material, but you can stop me at any time, all right? All right, here's the motivation. So as you know, today's SoC are mostly mixed signal. That means we don't see any SoC that are purely digital or purely analog. And what's interesting is that most of these SoCs are digital on the outside and analog on the inside. If you take these microprocessor and DRAM, for example, inside it may contain various analog circuits such as phase lock loop for generating clocks, regulators for controlling voltages, temperature sensors to shutting down the system before it gets too hot, lots of things. But they're embedded on the inside, and overall on the outside, they perform digital functionality and they communicate digital information. And because of that, most of the top-level test benches are written in SystemVerilog, verifying these digital functionality. And the de facto standard for performing those verification is to use UVM, the Universal Verification Methodology. So the problem is, hey, I want to use SystemVerilog test bench, but it contains the analog circuits. What do? You may say, hey, we can just verify them separately. Use Verilog for digital, use SPICE for analog. Turns out it's not that easy because these analog and digital parts embedded in these SoC are not that separable. So what I'm showing here is a simple example from a high-speed I/O receiver. You have a main, signal path propagating analog information, but along the way, you may have various digital engine, like either performing adaptation or calibration on the characteristics of these analog circuits. And often these, digital blocks or digital engine are, interacting with these analog circuits in a feedback loop, making it very difficult to separate and therefore verify one without the others. So what I want to do, and my goal is to verify this mixed signal SoC all in SystemVerilog. That means we want to keep our test bench in SystemVerilog because that's what we already have. And want to bring the analog into the SystemVerilog so that we can verify the whole functionality, including both analog and digital. To do that, I need to address two capabilities. One is, how do we simulate analog models in SystemVerilog, which is a digital simulator? And second is, how do we get these models, right? And if possible, we like to auto-extract these models from the existing analog circuits. And that's really the key topic of today. I founded Scientific Analog in 2015, and it's one of its main product is called X Model. And let me briefly introduce what this X Model does. It's essentially a plugin extension that works with the existing SystemVerilog simulator like VCS or Excellium. It enables fast and accurate analog mixed signal simulation. Okay? And the first idea when we started this company is that, hey, we have a Verilog that's really good at simulating very large scale digital system. And the key to that is this event-driven algorithm. If you take digital gates, the Verilog only does the computation for the gates whose inputs are changing, like from 0 to 1 or 1 to 0, and compute the output change as a result of that. It may change or may not change. And that event will propagate to the next, and you only evaluate the parts that are receiving those events. This is the key to achieving a really high efficiency in simulating large-scale systems. So the question is, can we extend that to simulating analog circuits? The basic problem is that if you take a very simple RC filter like this, even when the input is a single step, which is a single change, the output may change in a continuous time manner. And it seems like the outputs just keep changing. So to describe, for example, this exponentially decaying waveform, you need multiple events to describe its waveform. That's not event-driven, right? I want a single event. When there's a single event, I would just want to generate the single event at the output. And that way, I'll only compute the parts that are accepting the events, and I keep the simulation fast, even when the system scales larger. How do we do that? To that, we found a way. So the key lies in the way we express analog signal. So instead of using a set of points to describe this continuous time waveform, Xmodel uses a functional expression, which is this equation form shown on the slide. And whenever there is an event, we update this functional expression to describe how this waveform change over time. So each event is not just a value at a given point. It's really a functional equation describing how the signal change over time. And you don't have to generate new events if that expression is valid. And this expression here looks a little bit complicated. It's basically a sum of exponential function with a optional t to the m factor. And some of you may recognize that, hey, this is the general expression for the solution of a linear dynamical system. Yes, it is. And turns out, if you use this expression, you can easily translate that into a Laplace domain, which always take this partial fraction expansion form. It means if we have an input signal expressed in this Laplace S domain, we can compute the output response to some circuit or system by simply multiplying the input S domain expression with the S domain transfer function of that circuit or system. And the resulting expression is, again, the partial fraction form of the Laplace equation, which can be translated back into this expression we have. So it means that we can now do event-driven simulation for analog, propagating the input events to the output events. And this output event needs to be computed only once when there is an input event. Okay. So maybe I'll show a very short demo to illustrating this. So here what I have is a schematic describing a very simple model of a high-speed I/O. These little blocks are what we call Xmodel primitive. So for example, this is a clock gen primitive generating a periodic clock, which is triggering a PRBS generator, producing a random digital bits that get translated to the analog waveform with a finite voltage swing. It propagates into a channel, which inside has a filter primitive, which has these linear filter behavior. And we have another filter that models the equalizer that try to compensate the loss in the channel. And this environment is what we call Glister, which allows you to compose model in a schematic form. From that, you can compose a model and extract the SystemVerilog model just by doing netlisting. So here's the resulting netlist, which are described in the SystemVerilog format. And I can run this in SystemVerilog. So I'll just do it by pushing that play button. And here, as I said, Xmodel is a plugin extension. So it works with a like VCS or Excellium. For now, I'm doing with Excellium. And when the simulation is done, I can also view the waveforms of these signals. So data, the transmitted signal, received signal after the channel, and the signal after the equalizer. So what you see is the digital data, which is on the top, and the second one is the signal after the channel, and the last one is the signal after the equalizer. So as you expected, you see these very smoothly varying continuous time waveform because of the continuous time filter behavior. And what's notable here is that these markers indicate where the events have been triggered during the SystemVerilog simulation, which is actually very sparsely distributed. In fact, some of the events describe the waveform going down and up and then down because we have these expressions describing all these behavior. And the point where these events are being triggered is just exactly where the input events has occurred. For example, this event triggers this event, and that event triggers the event on the next stage, and so on. Okay, so this is very simple. This is a very simple example, but it illustrates that we can perform event-driven simulation for these analog models, all in SystemVerilog. Okay, there's some question. So Tony asked, like, how does performance and accuracy trade-off applies to X model? Well, typically in SPICE, you have those trade-off between speed and accuracy because SPICE computes the solution through iteration. So you keep repeating some expression until the error is small enough, and the accuracy determines how long you should be repeating that, to get to the answer. That means that if you want higher accuracy, you want low tolerance, then you have to iterate more. So that's why you have that trade-off. Here, you may have noticed that this computation is fully algebraic. I'm not repeating anything. There's no iteration. So speed is as fast as it can get, and it's fully accurate. So at least for the part that you're running simulation, there's no trade-off between speed and accuracy. There might be some other trade-off as we get to the model generation part. There's a choice where you can make whether you want a simpler model to run faster or more accurate model that may have a slower speed. And another question is Laplace transform. Yeah, Laplace transform with step is very easy, but how about complex input? So I'm just making things simple for you to understand. This input expression can be as complicated as expression because the output, which now has the same expression, can propagate to the next and next and next. And as it does, the expression will just be arbitrarily complex. And wow, I'm getting a lot of questions. How do the event dots are connected even when there are no events between the two? Okay, that's a very good question. So I just closed the waveform viewer, but I actually have the waveform here. Yeah, so how are they being connected? Right now, I'm using our own waveform viewer called XWave, which basically rendered this waveform using that expression information. So I'm using the XWave to just illustrate that we are really truly doing event-driven simulation. But X model can also generate more standard waveform format, such as FSDB, which will translate this expression into a set of points and store that into a file. So the easy answer is the XWave waveform viewer is actually computed expression to to basically plot the waveform between the 2 points. So that's happening by the waveform viewer, not by the simulator. Simulator just computes the equation itself. All right, so that's the event-driven part. But the analog circuits in general can be modeled in 2 different ways. One is you can use a set of blocks that are connected by signals that propagate in one direction. People call this a signal flow model. We call that, in a more simpler term, block level model. But turns out circuits in general may not be expressed in the signal flow model. For example, you may have a collection of these circuit elements like resistors and capacitor, and they're connected with voltage and currents, which may interact in a bidirectional way. And to determine their value, you have to solve a Kirchhoff circuit equation in a simultaneous fashion. And SystemVerilog, or Verilog in general, assumes that your system is a signal flow model, whereas SPICE assumes your circuit is always a conservative system model. Okay, and do we really need to support circuit level model in SystemVerilog? Turns out, yeah, we do, because it's the most natural way to model various analog circuit behaviors, including switching, nonlinearity, and loading effects. If you try to do this in a block level model, it's not impossible, but your model gets weird or unnatural. Okay. For example, loading effects, it refers to the effects that like bandwidth or delay of the circuit changes depending on what you connect at the output. So the information is actually flowing backwards, and that's not too natural to model in a signal flow model. So in X model, what you can do is, if you want to describe, the circuits using this conservative system model, like a network of circuit elements, you can do that. You can just list the elements one by one. Let's say a set of switches connected by the and capacitors, and this will work as is within SystemVerilog. So X model knows how to simulate circuits that are described as a network of these elements without SPICE. And how does it do that? So let me give you a brief idea on how it does it. So first, X model provides a set of primitives that we call circuit primitives. They basically correspond to the elements like resistors, capacitors, transistors, and diodes. And during the runtime, when it sees these network of elements, it performs partition of that network into a smaller unit we call clusters. And the way we partition the circuit into cluster is whether these clusters can be solved separately from the others. For example, in this simple example, we have a bias network that sets the bias for the load element for this common source amplifier, and the output drives a source follower to drive the final output. And what X model can recognize is that, hey, this first stage is a bias network, and its output can be determined without considering the others. So for now, I'm ignoring any cross-coupling capacitors between these stages. And it sees that, hey, once the bias input is given and input is coming, I can determine its output without considering the next. So that's another cluster. And the final cluster, the rest of the circuit can be just clustered into one, taking the result from the previous clusters and computing the final output. So it's a one circuit, but we can partition that into multiple clusters, which each cluster can be solved separately. And what you notice is that signals crossing these cluster boundaries are in fact traveling in a unidirectional fashion. So from the cluster, between clusters, what you have is a signal flow model. So now the remaining question is, how do I, describe the behavior of each cluster between input and output? Well, so what we do is, once the X model partitions circuit into cluster, for each of the cluster, it performs modified nodal analysis to set up the differential algebraic equation. And this is basically what SPICE does before solving the circuits. And then it will translate that into a Laplace domain transfer function between the inputs and outputs of each cluster. And once you have done that, then the process is the same as before. We've now got the transfer function between input and output. If there is a Laplace domain expression for the input, you can propagate to the output by multiplying with the transfer function. Okay, that's what X model does. Here's a question: how is the cluster boundary determined automatically? There is a various graph analysis. For example, channel connected component analysis or strongly connected component analysis. So well, given the direction of influence from one component on the other, you can identify a cluster where there's a cluster which only has a component that are influencing in a bidirectional way. So X model uses one variant of those analysis that is suited for our application. All right. And the next possible question you might have is, like, how do you handle nonlinearity? Like, how do you handle diodes and transistors, which have these nonlinear IV curve? The way we handle nonlinearity in general, especially in the circuit level model simulation, is we model them as piecewise linear models. So all these Laplace domain analysis are applicable when the circuit is linear. I mean, it's actually possible to extend it into nonlinear, but that's the out of scope. So the simple way of explaining this is that if there is a nonlinear circuit element, we divide its voltage or current operating region into intervals. You could call it operating region. And within each operating region, we model the element as a linear element, like having a linear relationship between voltage and current. For example, you take a diode, which has this, nonlinear behavior between voltage and current, like up to a certain threshold, it's off. But once the voltage across the diode is larger than the turn on voltage, you have a finite resistance between the two terminals. So we can divide these voltage range into intervals and assume there is a linear relationship between the voltage and current. We can extend that into a transistor. And the way we model transistor is a parallel combination of two nonlinear voltage controlled current sources. One of them is controlled by the VGS, the other is controlled by the VGD. And each of the characters is actually very similar to this diode behavior. This is in fact, it's called EKV model, and is also used a lot in European countries. Yeah. And this is how we handle nonlinearity, especially these nonlinear elements like diodes and transistors. So now that we have a way of simulating circuits within SystemVerilog, and we can also handle transistors and diodes. So it leads us to the first way of auto-generating model from a circuits, and we call that, which we call structural model generation. So it's very simple. You take a circuit, you identify all the spice element, composing the circuit. For each spice element, you come up with the equivalent X model primitive describing its behavior. Like you take a spice model, describe a transistor, convert that to equivalent N MOSFET X model primitive, and you do the rest for all the other elements. Once you have finished that, you connect the resulting device model using the same connectivity as in the original circuit. This is called structural modeling, and the resulting SystemVerilog model would just have the same set of elements as you see in the SPICE netlist, just such as MOSFET, resistor, capacitor, voltage source, current source, and so on. This is really like a mechanical way of generating models, but it works. Let me see a question. How can you model a real value switch in SystemVerilog using X model? Do we have any example of it? We do. So wait for a moment. I have a pipeline ADC example, which contains a switch capacitor circuit. So we'll see a lot of switches in there. All right. All right. And Model Zen is one of our products that does exactly that. It can automatically generate bottom-up analog model from your circuits or netlist. And by default, it generates this structural circuit level models. And when it does, let's say for your transistor model, it has to reflect any technology-dependent characteristics. So those model parameters are calibrated through SPICE simulation. And all of these models, in the end, you have these SystemVerilog model described with the X model primitives. So they run very fast in an event-driven way in SystemVerilog. Okay, so what is the simulated speed of the structural model versus block level model? Well, of course, it depends on the model, but for the example that I'm going to talk about, you see about 20x difference. Yeah, you'll get to that. Okay, so within Glister, we have a very easy to use interface where you can just click one button to generate model from the circuit. So let me just show you a short demo for that. I have on the slide is a two-stage op-amp. It's a very small circuit. And the way of generating model from the circuit is just press this button that says run model Zen. And when you do that, it will first extract SPICE netlist or Spectre netlist from the schematic. And it will parse that netlist into a set of circuit elements. And for each of the circuit element, so you see that it has identified NMOS, PMOS, capacitors, and diode. For each of the circuit element, it runs a small SPICE simulation to figure out its IV and CV characteristics. And it will fit the parameter for the X model primitive and combine those into the same connectivity to generate the final model. And that model gets stored into the X model view, in this Cadence Virtuoso. Okay. And here's the result. So the op-amp is described by a set of transistors, capacitors, and so on. And the parameter that you see here are describing the IV characteristics and the CV characteristics, of course, in a rather simplified way. But all of these numbers have been fitted just on the spot through the SPICE simulation. Okay? And the nice thing about this structural model generation is that I don't have to supply any information about what the circuit is, what condition is being used, what bias point it will operate in, or what kind of test bench I'll be using to test the result. I mean, all I need to know is what's making this circuit, like what kind of component you have in the circuit, and it just ran the individual characterization on each of the component. And I'm not going to do the demo on this to save time, but that resulting circuit can work in arbitrary situation. For example, this is an op-amp. So if I simulate it in an open loop, it will have a very large swing that could be clipped by VDD and ground, even when you supply a very small sinusoid. And when I take the same model and put it in a resistive feedback, now it will be linearized and have a gain between input and output determined by the resistor ratio. Okay, so that's the main advantage of using this structural model. Okay, so Tony's question, do we need to follow a specific drawing of a circuit, grouping, or wrapper? I'm not sure what you mean, but no, you don't. It's really literally, it could be a schematic that you have used to design your circuit drawn with PDK. Yeah, it's really your circuit schematic. Yeah, so yeah. Having said that, I'm going to just briefly flash this pipeline ADC example I'm going to use. It's a 8-bit pipeline ADC where each of the stage will quantize 1.5 bit. It's a very simple design. It's good for illustrating our point. And it's designed in a some fictional technology, 45 nanometer, and it's to support some analog operation. It's designed for dual supply. So the analog supply, oh, this is a typo. Analog supply is 3.3 and digital supply is 1.2. and it operates at 100 megahertz with a full-scale input range of 0.5 volt peak to peak. For the structural model generation, it's almost automatic, and there's just a few preparation steps to improve the simulation speed a little bit. For example, this design contains analog signal as well as digital signals. And for the digital signals, it's actually better to model them as the digital type, such as wire and reg in Verilog, or use our XBit type it's just another digital type used by XModel. Because when we build the test bench, we would like to use this SystemVerilog, which will supply the input using wire or reg signals. So it's possible for you to say, I want these to be bit, I want these to be XBit. So we'll do that steps as a preparation. And this design contains a lot of digital cells, and it's possible to use a simpler model for them to, again, improve the accuracy. So there is a technology configuration file where you can say, oh, these cells, which has a certain pattern, are digital cells, and so on. So we have a set of logic gates operating at 1.2, another one's operating at 3.3, and a lot of level converters between these two voltages. And we list them all. You can list their names or use these patterns to identify that these are digital gates. So quick question, are the cluster models, structural models encrypted? The structural models are not encrypted. I just show you the sources, as a result of the model generation. So they're not encrypted. The cluster partitioning is not shown to the user mainly because it can actually change dynamically. The boundary can change depending on which switch is conducting and so on. So it's actually hard to show, even if I want to. You'll see that later that this design contains like switch capacitor. So in those cells, all the transistors are actually switches. They're not really transistors. In those cases, you can say that, oh, model all these transistors as switches. That improves speed. So there's a way of identifying cells whose transistors are all really switches. Okay. And this is just showing example of the MDAC where all the transistors are switches. So we are listing them as one of the switch cells. Okay, so that's it. Once that is done, we just go to this circuit. Okay, so this is the schematic that I just showed on the slide. And generated model from this is just pressing this button. Yeah. Extracting netlist. Okay. This should finish fairly quickly because I have pre-run this. So what it's doing is caching the previous characterization results, and it's just going to pop up the model directly. So yeah. And well, it's now a big model because it contains multiple hierarchy in it, and which we're going to show one by one. So this is just a glimpse of it. So because this is a structural circuit level model, you will see their transistors one by one listed in their cells, and it generates a hierarchical model. So it preserves the same hierarchy as in the original design. And I have a simple simulation, which I'm not going to run right now. So first simulation just provides a input ramp as an input to the ADC. So what you expect is the digital output will also change in the similar fashion. And this slide just confirm it does. The simulation runtime is 19 minutes for 2 microsecond simulation. And these are the waveform of the intermediate stages. like the digital output and the visual output of the individual SubADC pipeline stages. I'm not going to go too much into that. And this is the result for the sinusoidal input. Again, it takes about 20 minutes for 2 microsecond simulation. All these glitches that you see are not code errors. They're momentary glitches because we're not really sampling the final output. And this is the waveform of the individual stages. Okay, so I just glimpsed through these waveforms just to show that this circuit level model, the structural model we generated just by simply clicking this button, runs as if it's SPICE. But what we are really running is SystemVerilog. Okay. So quick question here. What steps preparation to be done to export, integrate analog blocks into SystemVerilog, UVM verification environment? Very small. So all of these simulation are SystemVerilog simulation. So in order to take this into your UVM environment, all you have to do is to take this model and run it and supply some additional option, like include our primitive modules as one of your module list. And there is additional shared library for used by the X model primitive. That's it. So that's the goal of X model, do everything in SystemVerilog. Question from Rohan, can it parse hierarchical design? Yes, in fact, this design was hierarchical, and I will show you the hierarchy soon. And does it support EENet? It's not clear what it means to support, because right now I am showing extracting model from circuit. So there's, the circuit doesn't have EENet in here. So does it interoperate with EENet? Yes, it can, because it's just SystemVerilog. Oh yeah, so you may say it's, all right, okay. So 20 minutes, it's not as fast as you want. And in fact, the same simulation takes about 50 minutes in SPICE, fast SPICE. That's 2.5x speed up, which is good, but not as fast as you want. And yeah, so the key is, yeah, that will lead me to the next point is, the nice thing about structural model is that it enables a push button flow. And I generate model without really knowing what the circuit is doing. But the problem is that the model that we're generating is too low level. It's like listing transistors one by one. It's not too different from my SPICE netlist. So we're getting moderate speed up just because of the fact that we're using this event-driven algorithm, but I'm not getting any benefit of using like higher abstraction model. So now the next question is, can we generate higher abstraction functional models using this model Zen's push button flow? And what is functional model generation? Rather than focusing on the structure, it focuses on what the circuit does. And once you recognize what the circuit does, you can choose a model, the template model that describes that behavior. For example, for an amplifier, you can decide to model that, oh, I want to model it as a filter that has a finite bandwidth and use a polynomial function to describe some DC nonlinearity. That could be the template model of your choice. Then the next step is you calibrate the parameter used by this template. For example, the gain and bandwidth used by the filter and the DC characteristics described by this polynomial function. And you want to do that by characterizing the original circuit using SPICE and then annotate that information in this template. Can we do this in Model Zen? To do that, we introduced an interface called user-defined model. And it allows you to generate these higher abstraction model using the same flow of Model Zen. Idea is, we have not yet gotten to the point of auto-recognizing the functionality of the circuit. So we rely on users to say, oh, this part is a voltage reference. This part is an amplifier, okay? But when the users do that, Model Zen will model that as a voltage reference using a simpler model template whose parameters are characterized by SPICE. And the rest, it will just use a circuit level model. For example, let's say you have a voltage controlled oscillator that's made of 5 stages of buffers. If you model this as a circuit level model, you have lots of transistors that are constantly toggling. So that will generate a lot of events and slow down the simulation. So we can use UVM to say that, oh, this is a voltage controlled oscillator. It will generate a clock whose frequency changes by the input voltage. Then the model then will say, okay, I will measure the clock frequency as a function of the voltage, describe that as a piecewise linear function where all these characteristics are populated by spice. And then I use a primitive called frequency to clock primitive that will generate the clock with that frequency. Okay, another quick question for the bandgap reference, can it model temperature dependency? So it depends. So if you want, it can, but the default behavior, it doesn't. Okay, temperature is just one of the signal, and if you want to model the output changing as temperature, you treat the temperature as input and characterize is dependency and include that in your model. So that can be done. So and to illustrate the steps applying this UDM to your circuit, first you select the part of the circuit that you want to apply UDM mapping. Do a right mouse button click, select models and properties, and this window will pop up. And from here, you can select one of the UDMs that's predefined. For example, I want to model a continuous time linear equalizer. Then, and it will show the list of nets that are identified on the circuits. These nets are what we call pseudo terminal. These are the nets that are crossing the boundary of the selection. And for each of these pseudo terminal, you identify whether that's an input or output or VDD and ground. You're kind of identifying what each of the net does for this the circuit being selected. After that, that's it. You just push the same models and button, and it will generate the model. For the selected part, it will generate the functional model. For the other part, it will generate the circuit level model. Oh, okay. So Tony is actually going, way ahead, saying, can we identify a specific structure or symbol so that it will automatically identify that this is a reference generator, this is a amplifier, so on? Not yet, but one day we'll get to that. For real switch, how will the switch determine if the incoming signal is current or voltage? Okay, if the multiple voltage sources are connected to one, and so on. All right, so there's a simple answer to that. We don't have to identify whether the incoming signal is a voltage or current because it contains both. So when you see a network of circuit primitives, these circuit elements, X model solves voltage and current for every nodes and branches. So yeah, so all the cases you mentioned there will be handled naturally. That's why we're supporting circuit level model. So UDM is user-defined model, which means that you can define the things that you want to model. And it's basically a one Python file that defines these three elements. One is the set of terminals and parameters assumed by this model, like basically the one that you see on the screen, the list of ports, the list of parameters. And the second is the template of the functional model that this UDM should generate. Right? It could describe an amplifier, it describe a voltage source with a finite output impedance. And then lastly, the set of necessary SPICE simulation steps to fit the parameters used by the model. Okay, with these steps defined, now you can go and just map those UDM to the parts of the circuit, and you can generate the functional model for those parts. So now the question is, how many templates, how many UDM definition do we need to cover analog circuits? This is really the part that I wanted to address. Unfortunately, I'm running out of time, so I'll go a little fast. And surprisingly, for the circuit that take analog and inputs and outputs, we find that only a handful of templates are sufficient to cover most of the key analog circuits. That's a surprising result, and I'll explain why in the next few slides. Those are mainly the one-port model, multiple port model with impedances, and multiple amplifier model. Of course, there are other circuits, and they may have either digital inputs or digital outputs. For example, comparators and slicer, which take analog input, produce digital output. And of course, there are lots of digital logic gates embedded in analog circuits, flip-flops and latches. And there are circuits like delay lines, oscillators, that may look like they're propagating digital information, but you are really controlling their analog behavior, such as delay or frequency, sometimes duty cycle, and so on. So this talk, I'll mainly focus on these 3 template models, and which applies to the circuits with analog inputs and output. Starting with one-port model. This applies to circuit just producing voltage or current as outputs. Good example is the reference generator. And if you recall Thevenin and Norton equivalent circuit, you know that if the circuit is in linear, then a voltage source in series with the resistance or a current source in parallel with the resistance is sufficient. It's equivalent to any circuits out there. So we start from that. But in general, you may have a nonlinear behavior. For example, if this is a current source made of a transistor, depending on V out, you may have different current, and if V out too small, then the transistor will fall into a linear region, and it may eventually turn off. So to do that, each of these voltage and resistance can be a piecewise linear function, the same way we modeled the transistors in the previous slide. And of course, in general, to model any AC impedance, like AC dependent behavior, this resistance can be an impedance described in the S-domain transfer function. Okay? So that's our one-port model. And turns out even this simple model template covers a variety of circuits. And the key to that is each of our UDM can have a variable number of ports. So the number of ports for this UDM are not fixed. For example, the outputs coming out generated by these one-port model can be multiple. Like think of a circuit that generate multiple voltages, from a single circuit. There's a lot of that. For those circuits, you don't have a separate UDM supporting 1 output, 2 outputs, 3 outputs, and so on. You can have a single UDM covering all of them because those output pins can have a variable width. And another key element that enables the flexibility of each of these UDM is that each of the UDM can also support variable number of digital mode inputs. So it turns out many of these analog circuits in industry, they have lots of digital mode bits. They're either used for trimming, power down, enable, reset, selecting different inputs. And what you notice is that these inputs, they don't really change the functionality of the circuits. In other words, they don't really change the template describing the functionality of the circuit, but they rather change the characteristics. In other words, they change the parameter value. For instance, if the trimming bit changes, you're changing the output level produced by the reference circuit. For power down, you're turning that down to 0. Enable, you're producing some finite output or 0, or maybe VDD. So depending on those mode bits, you're just changing the parameter that control the output level, or sometimes impedance. So the way we handle those is that you can have an arbitrary number of digital mode inputs. And during the model generation process, Model Zen builds a lookup table that map each combination of the digital mode into a set of parameter values. That handles all kinds of digital modes. And no matter whether you have your BIOS circuit has a reset pin, power down, or additional trimming, the single UDM will take care of it all. Yeah. So for example, like this simple input model can model a DAC, digital to analog converter, because you can treat the digital input as digital mode bits. Depending on the value, you control the output voltage. Yeah. Even the RDAC and CDAC. All right, the second category of template is what we call multi-port impedance model. You see circuits where you have more than 2 ports, and between those ports, you have some impedances, either resistance, capacitance, inductance. And often you have these digital mode bits that change their impedance value. Because if it's just a simple RLC network, nah, just why bother? It's just a circuit level model, right? So typically it's like a setup capacitance controlled by the switches or resistors controlled by switches, or you may have a set of switches that are either selecting inputs, one input from the multiple inputs, or doing the opposite, like multiplexer and demultiplexer. In the second case, these multiplexing demultiplexer is again, depending on the digital input, you're changing the resistance between these ports. So again, it falls into this multi-port impedance model category. The third template is what we call multi-port amplifier model. For here, you now have some transfer function between the ports. Some ports are input, some ports are output. So for example, let's say an amplifier. Each port, whether that's an input or output, we use our one-port model to describe their finite input or output impedance, and maybe some nonlinearity if you want. And for between the ports, you can have these macro models that express the transfer function between the ports that can model DC gain, of course, AC transfer function, as well as nonlinearity, just again using the piecewise linear function. Okay. And these 3 basic template, although it looks very simple, cover a wide variety of analog circuits, and I will demonstrate that using the pipeline ADC example. Okay, starting with the BIOS generator. To save time, I'll just state briefly what this BIOS generator is made of. There is first stage is it generates a reference current from some external voltage. Then there's a middle stage that will just do some additional adjustment using the trimming bit. And the final stage will generate 3 bias voltages from that reference current. There are multiple ways of mapping this to UDM, but the simplest way is just to select the whole thing, say, this is a reference generator that will produce 3 voltages, VBCM, VBN, VBP, and these trimming bits are just digital mode bits. And the rest are either power and ground. Okay, that's it. And when we generate the model, we will get the functional model that will just produce, that has the same template I explained, and its output level will change as a function of the trimming bits. I'll first explain, if people are interested, I can show the actual demo of everything that I'm explaining right now. Okay, the second circuit that we have on this pipeline ADC is a sample and hold stage, which performs sample and hold on the input signal. And it's basically a switch capacitor circuit. And at the center of the circuit, we have a differential OTA with some common mode feedback circuit. And this differential OTA is a telescopic OTA with a boosted cascode, one of those circuits in the textbook. And it uses a lot of cascodes to provide large gain in a single stage, but the bad side is it consumes a lot of voltage overhead. So that's why we are using 3.3 volt supply in this design. So how do we model this? Yeah, well, again, it has these multiple transistor, it has these sub amplifier for boosted cascode, complicated. But we can map the whole thing saying, hey, that's an amplifier. And it has an amplifier with 2 inputs and 2 outputs. So notice the multiple amplifier model can have multiple inputs, multiple outputs. So it naturally extends to these differential OTA. It can actually extend to other amplifier that has auxiliary inputs, for example, like adjusting offsets. And for here, one of the bias input is actually treated as input because this is the signal that's being adjusted by the common mode feedback to control the output common mode at the desired level. So we recognize that, oh, this input can change during the simulation. So we model that as an input, one of the input of this amplifier, so that the output will actually change in response to that. So from the UDM perspective, this circuit is an amplifier with 3 inputs, 2 outputs. For common mode feedback, this is a simple switch capacitor circuit that will apply an offset to a common mode, the bias level that I just shown, if there's any error between the desired common mode output and their actual common mode output. For this one, it looks simple enough, and I'm not going to apply UDM. It's sufficient to say, oh, these transistors are all switches. And that's what we already done. For this switch capacitor design, there are setup clocks that should have a certain relationship between the two. For example, they must be non-overlapping. So for this one, we use a UDM, which I didn't really explain. We call delay line. This will generate a digital Verilog code that will have a delay between input and outputs. So when you map this input as in, all the other outputs as out, then the model then will characterize the delays between these input and outputs and use those delay number to generate the Verilog code that will propagate these digital input to digital output. And this is the simulation result of that sample and hold amp. So for the sinusoidal input coming in, output is a sinusoidal output, just that it's being sampled and held. The next stage is a SubADC. It's a flash ADC with 2 thresholds, where the register ladle generates 2 reference input. It drives a set of 2 comparators, which will compare the reference with the input and produce the digital output. Okay, Tony has a question about the nonlinear system model. Well, all the model that have transistor in it are essentially nonlinear system model. But at least for this particular example, well, ADC is basically, it's a circuit that tries to be as linear as possible. So, given that the design is good, it will, show very little nonlinearity. But still, if it can stick around, the waveform will show a lot of non-ideality, and including nonlinearity. So that could be that. We have other example, let's say for power amp in RF, that will have nonlinear distortion, like 3rd order distortion. And there are lots of examples on how we model that using a Volterra series. But that's not part of this talk. Okay, so back to the SubADC. So it's made of a resistor ladder followed by comparators. And a comparator is made of a preamp stage and a latch. In the preamp stage, I got lazy, and it felt tricky to apply UDM because it's not the pure amplifier, but it also contains a set of switches for offset cancellation and so on. So it's a mixture of amplifying behavior as well as switching behavior. So when things are tricky, you just leave it as is. Then the circuit level model will take care of it. So there's always this safety net of using models then, because we can support model generation for arbitrary circuits. For the comparator, the last stage, now this one we can apply a UDM, which is a comparator UDM, which will take the analog input and produce the digital output based on the analog sample triggered at the rising edge of the clock. So Hardy's question is on RF. How do you model IIP2, IIP3? I think that I better take that offline. And if you can stick around after this talk, I can show you some examples. Okay, so following the SubADC output, which will be thermometer coded, we have a set of encoder logic that will either translate into a one-hot code or a binary code. So that's basically a digital gates. And of course, analog circuits may contain digital gates. And we have a UDM called combinational logic that can model arbitrary combinational logic. So you can just group the whole thing, say, just figure out the combination logic between these inputs and outputs, and it will just build a lookup table between inputs and outputs. You can do that the same for the second encoder, and well, it's possible to specify different levels, like different voltage level for the inputs and outputs, which means that it can also cover level converters, which propagate digital information but translating different analog levels. We also have a UDM for flip-flops, which can auto-identify whether it's a rising edge trigger, falling edge trigger, whether it has a set and reset, whether those are synchronous and asynchronous, so on. So if you group a D flip-flop and will identify its type and generate the equivalent Verilog model for that circuit. Now, this is a simulation result for that SubADC. Input is slowly varying from low to high volt value. As it does, you see the digital output switches from 0, 0, 0, 1, and 1, 0. And these are the outputs of the encoded output, which is a one-hot code in this case. Now, the next stage is MDAC, in short for multiplying DAC. This is again a switch capacitor circuit. It will take the digital input and analog input. For the digital input, it will translate that into an analog signal through a DAC. And it will take the difference between the two, like do the subtraction, and multiply the result by a factor of 2. That's what this MDAC does. And for this circuit, now we actually already model all the subcomponents, like the OTA. Looks like that's it. And here, it's just a set of capacitors and switches. So we'll just use a circuit level model. And this is a simulation result for that MDAC. For different digital code, you can see that there's a different offset being applied to the sinusoid input. So for the mid input, you see a symmetric sinusoid up and down. For the other input, you see the skewed symmetric output, sinusoidal output. Sorry, I'm going too fast. So finally, there's a ADC unit stage that will digitize 1.5 bit information from the preceding stage and propagate the residual information to the next stage. So what you notice is that once you model the basic components, as you go up to the hierarchy, you just see the collection of these components, and there's nothing additional to do. Just keep pressing the models in to generate model. And here's the simulation result for that MDAC. So as the input gradually changes, the digital output also gradually changes, and the residual output shows, this sawtooth transfer function, which is expected from this stage. When this pipeline ADC, when each of the stage in the pipeline ADC produces the individual digital output, you need a circuit that can combine these individual digital output and produce the final digitized output. So the one thing it needs to do is it needs to align the timing, because they're all coming out at a different timing, and you have to do a summing. So this could be described in Verilog. We have an example for that. But for this has a very regular structure, and many analog designers will actually do this by hand. And it's also possible to extract the equivalent Verilog model from this using UDM. So this is actually only made of a full adder and a D flip-flop. We already applied UDM for the full the D flip-flop. So for the full adder, hey, that's a combination logic. So we just apply a combination logic UDM, identifying its input and output. That's it. Now we go to the ADC top, run. So for that one, because it's the last one, I will do the demo. So this is a circuit that I just explained with all the UDM mappings that I explained. And to generate model, press that button. Okay, so the list of elements, it went really fast, but it's slightly different than before because instead of just identifying individual circuit elements, it's also identifying the UDM that we have mapped, like delay lines, amp linear, and so on. Okay, so it's actually characterizing the UDM. Maybe we'll take a look at the model. And so it's a hierarchical model. So you see multiple modules, spanning the whole hierarchy, and probably you'll identify some UDM here. Okay, so this is a UDM, the model generated by the UDM for the reference generator. And remember, it had 3 bits of trimming bits. So it has constructed the lookup table that will set the output DC level, output resistance, output capacitance for each of the mode input combination. And in the end, there will be, went too far. There will be a kind of a macro model driving the output voltage with these the output resistance and capacitance, whose value are controlled by that lookup table. And we have 3 sets of them because we have 3 outputs. Okay. Now let me run the simulation. So previously the circuit level model ran for about 19 minutes. This one runs much faster. I'm over time, but this is almost done. So please bear with me. Apologies. Yeah. This is actually also a good time if you have any questions, because I'm going to wait for about 45 seconds. Yeah. Okay. Oh, well, exactly 45 seconds. Okay. Now here's the simulated waveform. So this is for the RAM input, and the digital output is also gradually changing from 0 to 255 because of the 8-bit ADC. These little glitches is not an error because in a pipeline stage, when you start, there can be some bogus internal state in the intermediate stages. So those are being flushed out here. And these are the waveform for the intermediate stages. So for the first stage, the code is gradually increasing, and these are the residual output, propagating to the second stage. In the second stage, you see those codes like going through these patterns because now there are lower significant digits. And you see those patterns, having shorter periods over time because they're toggling more frequently. Okay. All right, so that's it. So let me summarize. So I just demonstrated 2 ways of automatically extracting bottom-up model from analog circuits. And those 2 ways include structural modeling, which taking the elements from the circuit as is, and then translate that and just connecting them up using the same topology. And the nice thing about that is it guarantees correct by construction models for any kinds of circuits. And the second approach I talked about is functional modeling. And I came up with a set of templates, which are not that many, but hopefully I demonstrated that it can be applied to real circuits like pipeline ADC to deliver a much faster speed than using a pure circuit level model. And well, it's not necessary for this functional model to apply to all the circuits. You have seen me saying, hey, this circuit is tricky. I'm just going to use the circuit level model. And I'm only going to use the functional model for the circuit that looks easy enough or that affects the speed much. So the best results are often achieved by combining these two approaches. So in the end, what we got is the SystemVerilog model for the analog circuits. As someone asked, this SystemVerilog model can run in the SystemVerilog environment, UVM environment as is. So now you can perform efficient verification for your SoC, including these analog circuits, all in SystemVerilog, like in UVM. That's it. And thank you for your attention, and thank you for your patience. Me going over time. Yeah.
Thank you very much, Jaya. Thank you for showing us what's going on under the hood, basically. And a great talk as always. We do have two questions. I don't know if I think we don't have anything. If people want to leave, feel free. And there are two questions. If you do have time, we can get to those.
I have time.
Sure. Do you want to answer those questions?
Okay, I can share my slides. So I will send my slides to Shahab, and maybe you can post it somewhere.
Yeah, we will post it online as soon as we can. And there is a question about incoming signal being current or voltage.
Oh, I think I addressed that. So my answer was because we can just handle circuit level model that really uses the Kirchhoff equations to solve all the node voltage and branch current. We can handle all the cases that are being mentioned here, like multiple voltage sources are being connected to one point and being switched, or they're having a multiple voltage drivers. These are all troublesome when you try to model those in a signal flow model. And I assume Saurabh is coming from experience with the real number model, where to address that, they introduce it's called user-defined net and a resolution function to how to determine the output when there are multiple things driving a single node. You don't have to do any of that. So if you have multiple voltage sources, merging into one through some resistors, then it will determine by those impedance ratios and so on. And Tony's, does my company provide trial version? Yes.
Okay, thank you very much. Thanks everyone for attending, and thank you for your presentation. I think this was the last question, and we can wrap up the presentation today. Thanks.
Yeah. So Hardy question RF. I can send. In fact, we have a paper describing how to model nonlinearity of RF power amp. I think the best way is for me to send you that paper. So if you can send me your email address to my email, like this is my email address, jeha@scianalog.com, then I will forward that paper to you. Or if you need any additional explanation, I can set up a meeting with you. Does that sound good?
Yep, thanks.
Right, thank you.
Thank you, everyone.